For the first time ever, we have the capability to detect life. We took some complicated biomolecules and put it in sulfuric acid to see what would happen. And lo and behold, we found a lot of biomolecules are stable in sulfuric acid. So calculations tell us that there's probably as many rogue planets as there are stars. I'm going to definitely incorporate that when I get asked this question next time.
Welcome to the 20th episode of Apple Finch Pudding, your gateway into the world of science. Today's scientist is Sara Seager, a professor in physics and planetary science at MIT. Amongst other books, Sara literally wrote a handbook on the physics of exoplanet atmospheres. Her work on exoplanets has earned her numerous awards and distinctions, including an honorary PhD from the University of Toronto earlier this year, and an appointment to the Order of Canada in 2020, which is one of Canada's highest honors. With such a resume, it's hard not to be impressed. So welcome, Sara, and thank you for being here.
Thanks for having me.
Before we start, do you have a fun science fact for our listeners?
Well, I have a brand new science fact, which maybe we can unpack a bit later. But we have discovered that some complicated biochemicals can survive in sulfuric acid, which is an incredibly strong acid that makes up the clouds of Venus.
Okay, that is insane. And that is something I wanted to talk about Venus later on. So no, we'll start with the other stuff first, and then we'll get into it. So you'll get back to me with more details about that. We will start with the basics. So you work on exoplanets. Exoplanets are planets outside of the solar system. But how do you look for them?
Well, we have so many ways to look for exoplanets, 6 or 7 different ways. But I'll tell you the most popular one we have today. Well, all the stars in the sky are just point sources of light. But if they just happen to have a planetary system, and if that planetary system happens to be lined up just perfectly so, edge on, we might see a planet go in front of the star. And actually, because the star is a point source of light, all we're going to see is a tiny drop in brightness. So tiny, we couldn't see it with our eyes. But our special cameras on our telescopes can pick it up. And what's amazing about this technique, we call it the transit technique, is at least one astronomer thought about this in the 1950s. His name was Otto Struve, and he wrote a paper about it. And he kind of outlined all it was, but back then there's no way they had the precision to measure brightness drops of 1% or smaller to find planets. Plus, a planet being edge on, a planet having its orbit edge on, as seen from our viewpoint, is extremely rare, actually. So you have to monitor many stars, tens of thousands of stars, to find these so-called transiting planets.
Wow. And based on that dimming in light, do you also know, for example, how far the planet is from the star?
We do. If we see multiple transits, more than one transit, because the planet transits every time it goes in front of its star, we get a period, like the year, the orbital period. If we know the mass of the star, then we can use Kepler's third law, which relates the mass of the star, the period, and the semi-major axis. And it's a little more complicated for planets on an eccentric orbit rather than a circular orbit.
And how do we know that mass?
Well, there's a lot of different techniques, but sort of on the whole, think of it like having a library of a star type. We can tell what kind of star it is by its spectrum of light. And we have other ways like binary star systems where we can disentangle various things and understand what the mass of a star is according to its spectral type.
So based on the spectral type of the star, we know its mass. And based on that mass and the period of the planet orbiting, we can determine how far it is from the star.
Correct. More about its orbit. Just so you know, we have thousands of planets have been discovered with the transit technique. Probably the large majority of planets we know about today. And I can tell you a bit more, like if you want to know more about how we do it, I can tell you a bit more about that.
Yes, please go.
Well, I used to have a leadership role on the MIT-led NASA mission TESS. TESS is basically what it is it's 4 glorified telephoto lenses. So think of like a lens attached to a CCD, so attached to a detector. And each of these 4 cameras, they don't have a very big aperture. They're only about 10 centimeters in diameter. And they're all bolted to a platform on a spacecraft that orbits Earth. And the spacecraft's in a very special orbit. It actually is in a very elliptical orbit about Earth. So it spends a lot of time away from Earth observing the sky. And it actually observes the sky, each patch of the sky, for a month. And TESS monitors let's say it monitors tens of thousands of stars at once. In fact, it actually monitors millions of stars. And all that data comes back to Earth. And it gets analyzed by two different pipelines. Our official data pipeline is at NASA Ames, and we have one at MIT as well. And a bunch of different things have to happen to the data, but essentially what we end up getting are light curves of the stars. So it's like, imagine pointing your phone at the sky and taking an image every minute, okay? And you have all those images, and the computer finds each star's center, and it measures the brightness of each star for every frame, and then creates a light curve, the star's brightness as a function of time. And then we have other algorithms that search for a tiny drop in brightness that might be a planet. But there's a lot of false positives, so the computer has to do a lot of hard work. At the end of searching through tens of thousands of stars, or for another pipeline, millions, it spits out a few hundred kind of likely planet candidates. And those go to a group of humans. We call them vetters. And we train people to be vetters, and people look by eye, and a group decides together, based on a lot of auxiliary information, which ones can be lofted to planet candidate status. And once they're labeled a planet candidate, they go out to the community, who have to use a lot of different ground-based telescopes and other tools to find out which ones are indeed planets.
So there's also a lot of sharing of that data within the community.
In fact, the NASA TESS mission, all the data is public immediately.
Oh, really?
When we first set up all the pipelines and did all the work, even though we're running the mission, we're not allowed to analyze the data scientifically until it's made public. It's a NASA rule because it's taxpayers' dollars that have funded this mission. And so the data, it only takes, I want to say it's about a week now from when the data hits the ground to when it's made available to the community.
Well, that's really fast as well.
Very fast. I mean, it was supposed to be 2 months. That was kind of our initial plan. But we managed to really speed it up and get some of the less analyzed, not necessarily the planet candidates in a week, but, getting some data products out there.
That is also a general trend in science, right? To have data more publicly available. But some people are quite hesitant about that because they're afraid people might scope their data or something.
Right. Well, there's two kind of different camps. One big push in the United States now from our Congress is because it's taxpayer dollar, it should be available immediately. And for projects like TESS, where we have hundreds of planet candidates a month, well, we used to anyway, we want people to work on those right away. We also have another push coming from journals. When you want to publish a scientific paper, you put it in a journal, and they want you to put all your data public when it's published because, we want reproducibility here. Mm-hmm. And they want you to put your raw data as well as, your analyzed data. So there's those two separate camps. But I agree with you. Some people are upset because if you're a student just learning how to use the data and how to analyze it, you'll be pretty slow. But that's an investment for your future. So it's fine. But if a more senior person or more experienced student or more experienced person comes along, they can just analyze it immediately and get a result. So far, people are kind of on good behavior, but you never know what could happen.
No, that's true. That's true. Okay. And so there's a relationship also of the planet between its mass and its radius. How do they determine the mass and the radius?
We get the radius of the star from this drop in brightness because the drop in brightness is related to the planet to star area ratio.
So if we know how bright it was at first and how much it dims, based on the dimming, we know how large the planet is, and we can infer the mass from that.
No, sorry, that's not right. So we get the radius that way, but we need a totally independent method to get the mass.
And how do we do that?
Well, it's called radial velocity. So there's a star, and imagine the planet orbiting the star. Mm-hmm. And due to gravity, the star actually wobbles a bit. Mm-hmm. But in fact, what's really happening is the planet and star are orbiting their common center of mass. So they have a common, it's like a seesaw. If you were a child and you go on a seesaw and there's this pivot point. Yeah. So we can measure the line of sight motion of the star as it's wobbling.
Okay.
You can measure that line of sight motion so well, literally, to walk to your walking speed, literally to meters per second or even less.
Well, that's amazing. And now about, what distance are we talking about? Because that's really small changes.
The stars are many light years away. The stars are tens to hundreds of light years away. But from this, we have to infer how much is that star wobbling, like in all its, it's 3D, not just the 1D along the line of sight. And it's kind of complicated. Usually it takes 2 classes for me to explain this to my students. So
Okay.
hopefully you can just adopt this, that we can back out the mass of the planet. So if we have a way to get the mass and size, remember mass over volume is density, we can get the average density of a planet. And you might think, okay, it's done now, we can figure out what it's made of. Well, we can if it's really rocky, or we can if it's just like a pure hydrogen helium planet, but there's everything in between. Planets have come in every single average density imaginable, and that was a huge surprise for us.
Can you give us some examples of that range?
Well, let me give you this little thought experiment first. Imagine if I come to see you in person and I give you a box, and I tell you this box has 3 things in it: rock, water, and air. Or let's say rock, water, and helium. So if you take that box and it's so heavy, whoosh, like you have to drop it because it's so heavy, you weren't expecting that. Can you guess what might be in it? What the dominant component is? Remember, you have iron, water, and helium gas.
Then I would guess iron.
Right. Okay. So if the planet is extremely dense, you can guess what it's made of. Now imagine if I give you that box and you let go for a second and it floats away. You can probably guess it would be made of helium.
Yeah.
But now imagine I give you the box and it's just average. It's so average. You know it's a mixture, but it could be just iron and helium. Or maybe it's just pure water. So our problem is that many planets just sort of end up in this middle area. We don't know which combination. Maybe each planet has a different combination. So that's a problem. But what's even more peculiar is that many of these small planets 2 to 3 times the size of Earth, they ended up definitely not being pure rocks. Instead, they're much lighter. They're not pure helium either, but they're so light that we don't understand them at all. We have no solar system counterpart. And no one knows how they formed or why they even exist, actually. And they're planets 2 to 3 times the size of Earth. Our Neptune in our solar system is 4 times the size of Earth. But these things that would be just so weird. We don't know how Neptune formed, really. We call them mini Neptunes, just for lack of a better word, because they're not predominantly rocky, but we don't know what they're made of. Some people want to believe they're water worlds. But just like the example I gave you of the box, this is sort of on the lighter side, but we haven't figured it out yet.
Okay. But they do contain some type of rocks. Or
Probably.
we're not sure. Yeah.
Almost certainly, just based on how we think planets formed and their density, they probably have some kind of rocks, correct?
And when we look at planets or exoplanets for extraterrestrial life, there's often a focus on the Goldilocks zone. So that's the habitable area. Can you explain the Goldilocks zone? And is it possible to have habitable planets outside of the Goldilocks zone?
So there is this zone around each star. Think of it like a giant kind of circle or like annulus around each star, where a planet, as heated by the star, would be the right temperature to have liquid water. All life as we know it needs liquid water. And so we call this the Goldilocks zone. So the planet is the distance from the star that's not too hot, not too cold, but just right for life. We also call it the habitable zone. There's definitely ranges outside of that zone where life could exist. So some of these planets, some of the rocky planets, if they're far enough from their star, and they might be able to have a lot of hydrogen atmosphere. You know, hydrogen is the most potent greenhouse gas out there. We never hear about that because we don't have hydrogen on our planet in our atmosphere. But if you imagine a planet with like a massively strong greenhouse gas, it could be warm, very far from its star, actually. And people have made calculations and they've said you could have a habitable planet at the Jupiter sun distance, 5 times the Earth sun distance, or even further, even up to 10 times, if it had this hydrogen atmosphere, like a very strong greenhouse.
And why don't we have hydrogen in the atmosphere?
Well, in our planet, we think Earth might have been born. We think all planets are born with some hydrogen in the atmosphere, but it's so light that it escapes our atmosphere. Just like, were you ever a child with the helium balloon? You know, and you let go of it by mistake and then it floats away. It's like that. It'll just float away and eventually leave our atmosphere.
And can hydrogen be produced from water?
In fact, it can, as sunlight splits water vapor apart. Hydrogen and oxygen are now independent, but they come back together again. So we do split up some, but we have water oceans and rain. And so a lot of our water does stay in the atmosphere. It doesn't all get split up because we get clouds. and the clouds rain, and we have this water cycle. But some water definitely gets split up. We do have some hydrogen escape, but not that much.
Okay. So it's not like we're going to lose our hydrogen or like the hydrogen from all the water on Earth will not be lost.
No, but there's some peculiarities of our atmosphere because we form clouds. Mm-hmm. But if our atmospheric temperature and pressure was different and we didn't form clouds, we definitely could lose our water.
You also have rogue planets. So that's planets without a star. Are they abundant and can they have life actually?
Well, there's two separate things there. We think that every planetary system forms with too many planets because planets want to form. They're like easy to form. But we can't, there's not room enough for all of them, gravitationally speaking. So calculations tell us that there's probably as many rogue planets as there are stars.
Oh,
yeah,
that's a lot.
It's a lot. And, we haven't for sure 100% seen any of these yet. Small, like solar system type planets necessarily, so we don't have, proof of it yet. And the only way they could be habitable is if they would have to have like this giant blanket of hydrogen to keep the planet warm. And energy might come from radioactive decay from the interior. There are more massive, hotter free-floating planets we have seen. And we think these planets form like failed stars. So they never had a sun. They were supposed to be the sun. And they just kind of didn't have enough juice. They were too low mass. And so there are these free-floating planets. But they're effectively like Jupiter. They have no surface as we know it, and they almost certainly don't have life.
How does that work or come into existence, a failed star? How does a star fail?
The way that stars are formed is there's a giant cloud of gas and dust, a giant spherical cloud. And it's a bit unstable. And eventually, I don't know exactly how, but it gets perturbed. And parts of it start collapsing, like all over the place. Little pieces collapse. Not the entire cloud, but just different pieces. And when the pieces collapse, eventually they form a star because they ignite hydrogen fusion on the inside. But some of them, just a little tiny piece collapsed, and it was just too small to have enough mass to make it into a star. And we call that a failed star.
Okay, that's really cool. So yeah, we're looking for life. We have checked the Goldilocks zone. So Drake's equation tries to estimate the abundance of extraterrestrial life. Could you explain how that works and how it's related actually to your equation, the Seager equation?
Sure. Well, the Drake equation is a bit of a misnomer because it's a bunch of terms to help illustrate, in his case, the search for intelligent life that would be communicating to us by radio signals. So we're imagining there's life out there like us that has built radio telescopes and is sending us a message. And so there are various terms in there. Some terms, we know what they are. They're like, how often do stars form and how many planets are around other stars? We know those numbers. But the Drake equation, the latter few terms, we just won't know the number. We have to make a guess, like how many intelligent civilizations are out there? How long do these civilizations last? I took the Drake equation and I made a different version to explain the modern day search for life by way of gases in the atmosphere that don't belong. And I asked Frank Drake while he was still alive if he minded that I took his equation and reused it. And he said it was okay.
You had his permission. So you're fine.
But I already did it because, I didn't see him that often. So I already made it. I got his permission after the fact. So then I redid it in terms of, again, it's not a predictive equation, but it's more to help you understand all the things involved. So if you think of doing a search for signs of life by way of gases in the atmosphere that don't belong, mine starts out with how many stars are in your survey. And then it's like, are these stars, like, would a planet be transiting in some cases? And there's sort of different probabilities. But like the Drake equation, the first few terms, we can put a number to them. We know how common planets are. We have a good guess for how common planets are in the habitable zone. The latter few terms, we don't know the answer to. It's like, how many planets have life? What fraction of planets that can have life do have life? What fraction of that life generates a gas that we can detect from far away? And so the Seager equation is a revised version of the Drake equation to help explain to you, all the different factors involved in the search for life beyond Earth.
Okay, and also one thing you already mentioned, I think is really interesting, that when we look, for example, for planets, that they have to be between the star and our line of sight to be observable. But that's something that we
The
don't
transiting
think
planets.
about.
We have a
Yeah.
lot of other planets with different techniques we can observe. But the
Okay.
transiting planets are the easiest to find and the easiest to observe their atmospheres. So they are our main focus today.
Okay, but we don't have to get into the details if you don't want, but there is a possibility to watch for planets that are not in our line of sight between us and their star.
That's right.
And the fact that we haven't yet observed extraterrestrial life, while we think it might be abundant, is Fermi's paradox. Can you, or what is your most likely explanation? And also, do you think extraterrestrial life is abundant or not?
Well, it's really hard to say. I mean, we see the ingredients for life everywhere. So everywhere we look, we see molecules, complex, even in the interstellar medium between stars, there are complex molecules. So we're confident that the ingredients for life are out there. But whether or not life makes it to that intelligent stage where it wants to communicate to us, that's like a whole different thing. My favorite theory about why, if life is abundant and it eventually evolves to intelligence, my favorite theory is I liken it to like the ants. You know how I'm sure you've had ants in your house, and they're pretty clever in a way because they go on a reconnaissance mission, right? Like they're looking around for food. And if they find something, like if you've ever left cat food on your counter, then all of a sudden in the springtime, when they're figuring out what to do, you get a whole flood of them. There's like an army coming to like get the food. Yeah. So they're kind of intelligent in their own way. But could you ever talk to an ant? Like, could you ever communicate like what a podcast is or the stars at night? Like, how on earth would you even do that? You can communicate by wiping up their trail, and then they get lost for a while because they don't have a trail.
Yeah.
So I liken it to that. I think we're the ants.
Okay.
And there's intelligent life out there. They're just like, how would they communicate to us? Why would they want to? How would they tell us about all those complicated things they know about? I'm not saying that's the truth. That's just my favorite idea.
So they are able to observe us maybe, but they have no way of communicating because they're maybe too advanced for us.
Maybe, or maybe they don't want to because we're like the ants.
Oh, yeah, that's also a good possibility. A few years ago, you were on Lex Fridman's podcast where he talked about the fact that we might be able to detect life within 1 or 2 decades. We're only 3 years later, but are we any closer?
Well, we are closer. A really big thing has happened. And that is, for the first time ever, we have the capability to detect life beyond Earth, signs of life anyway. And that is the James Webb Space Telescope, the NASA ESA CSA telescope that launched after my podcast with Lex. So it had a lot of delays. Launch is always very scary. No matter what you do, there's always a chance of the telescope blowing up. But the telescope launched successfully on December 25th, 2021. It made its way to its orbit very far, 1 million miles away from Earth. It's successfully operating now. So that's the thing that has happened. But we have 2 issues out here now. This telescope can observe exoplanet atmospheres and search for gases that don't belong that might indicate life. But the problem is we only have a very small number of planets that the telescope can observe for us in that range. I mean, it can observe hundreds of planets, but the small rocky planets, it's very tricky. And the small rocky planets, it can't study rocky planets transiting sun-sized stars because our sun is so big and the planet is so small. But the Webb can monitor small planets transiting small stars. There are a lot of small red dwarf stars out there. But these red dwarfs, they don't behave like our sun. I like to say they have a very long, bad teenage phase.
Okay.
Because when a star starts to fuse hydrogen to like make energy, it takes a while for it to see. Like if you ever start a fire, sometimes the fire takes a while to get stably burning with wood.
Yeah.
Sometimes you have to try a couple times. It's like a bit weird. Well, these M-Dwarf stars, they have a long period of time where they're giving off a ton of energy and a lot of high, strong radiation, a lot of high energy particles. And some people think during that time, it could have just blown away the planet's atmosphere. Okay. Right, for the small planets transiting small red dwarf stars. So we're not 100% sure if they have atmospheres. So we have those problems. And we have one more problem. And that is these M-Dwarf stars, they're very active. They have a lot of spots, star spots that are changing with time and evolving. And that turns out to make it really hard for us to study the planet atmosphere because the background star is changing in a way that so far is stronger than the atmosphere signal we're looking for.
Okay. Yeah. So the change in wavelength and intensity is stronger than the signal of a planet moving in front of the star.
So far. And we have to solve that problem. We have to figure out how to mitigate, how to get rid of or work with that background variability. So we have those issues, but the good news is, wow, we can even talk about this. We have real data on rocky worlds, atmospheres. We have the telescope that's operational. And that's why I said 10 years. That would have been, let's say, within 5 to 10 years. And there's other plans afoot to build other telescopes to go out there. They might take a bit more than 20 years, unfortunately.
Can you tell us a little bit more about that?
Well, we're going to move beyond transiting planets now. And I want to think about a true Earth twin orbiting a sun-like star. And to find these planets, not transiting necessarily, we have to send a space telescope above the blurring effects of Earth's atmosphere. And this telescope has to be able to block out the starlight so we can see the planet directly. It's a very, very hard way to find planets.
Yeah.
We call it a coronagraph, which is named after a French optical physicist who in the 1920s wanted to observe the sun's corona. The sun has this beautiful, like, high energy plasma, and you can see it during a solar eclipse when the moon blocks our sun. But he wanted to see it on any given day, not just during a rare solar eclipse. So he invented a method to block out the sunlight so we could see the corona, hence it's called coronagraph. And people are thinking of, well, we have developed a lot of different ways, not me personally, but the community, to block out the starlight to see planets directly. But we do have a bit of a long way to go. But NASA has put a space telescope with the coronagraph as the #1 priority for our next giant flagship space mission.
Okay, and what would that change for our observations? So it would change a lot, I assume, but...
A lot, because the James Webb Space Telescope today can observe transiting planets that are small and rocky, orbiting small stars. These M-Dwarf stars that have a lot of activity in the crazy teenage phase. But if we want to be able to extend this search to non-transiting planets and true Earth-Sun twins, we need this whole other telescope. So it would open up a whole new area of planets. And ones that, you know, based on our own Earth, we have a better chance of assuming have an atmosphere and have some way that we can at least hope that they're logically more like ours.
And I know it's impossible to give an exact number, but do you have some idea how frequent or how abundant Earth-like planets would be?
We don't, unfortunately. I mean, some people like to speculate 1 in 5 stars like our sun has a planet might be like Earth, but that's based on some very generous parameters.
And so also when we look for those extraterrestrial planets, we look for biosignatures. So that are the gases that you were talking about. But how do we even investigate the atmosphere of an extraterrestrial planet?
Well, for the transiting planets, as the planet goes in front of the star, some of the starlight shines through the atmosphere. And if we look at the star by itself, and then we look at the star when the planet's in front of the star, actually, the light we're getting looks different because some of the starlight has been blocked by the planet atmosphere.
Yeah.
And we do that as a function of wavelength, and we can actually tell what gases are in the planet atmosphere.
Because of the immense distances, I assume so we are focusing our apparatus on a star. We get an image, but like the star with its planet is maybe a pixel or less.
Right. We don't resolve it in any way. It's just a point of light.
Okay. Because otherwise I would think you have like some kind of mixed pixel problem, right?
Well, you do, because we know that our atmosphere is different, right? You can go to different parts of the globe and the temperature is different. Near our surface, we have water vapor, but as you go up in the atmosphere, you have less water vapor. But we can't help that. You've asked a great question there because everything's all averaged together. It's less than a pixel. So we work with that. We're just sort of looking for the global average, let's say, of gases.
For example, in our atmosphere, we have 20% of oxygen. That's something I assume you would be able to detect, but how abundant does a gas need to be able to detect it?
It depends on the gas, actually. I want you to think of like a skunk smell. You only need a tiny bit of skunk spray to have a very bad smell.
Okay, yeah.
And carbon dioxide, that's our that's one of our strongest greenhouse gases on Earth. We have 400 parts per million of carbon dioxide in our atmosphere, but it's still creating a lot of trouble. So some gases, you can have a tiny amount and it makes a huge difference. But typically you'd need part per million or hundreds of parts per million of a gas to make to register.
Now, I would also like to talk at least briefly about one of your papers, and that actually brings us back to our opening, because the title of the paper that you co-authored was Phosphine Gas in the Cloud Decks of Venus, a paper from 2020. This has actually, you recently tweeted about it, that this has resulted in some back and forth, some ping pong between different science groups. Could you give us some more insights on that discussion?
Yes, I can. So I'll just briefly tell you how I got involved with phosphine on Venus. One of the things my team does is we work to think hard about what is a list of gases that could be a sign of life on an exoplanet if we're able to detect it in an exoplanet atmosphere in the future. And one of our favorite gases is phosphine, because on Earth, phosphine is only associated with life. We humans make it as like an insecticide or pesticide. And phosphine is found in oxygen-free environments like wetlands and animal guts. And it's also found in laboratory cultures of cells, mixed cultures. So it's pretty amazing because on Earth, phosphorus goes with oxygen, not with hydrogen. Phosphine is a phosphorus atom and 3 hydrogen atoms. So it seems like a great idea for gas. It's so thermodynamically disfavored, like it takes energy to make phosphine. So it's not just going to lie around on its own. And we already talked about how Earth hardly has any hydrogen. So I was working on this for exoplanets. And meanwhile, someone else across the globe, Professor Jane Greaves in the UK, was searching for phosphine as a sign of life in the Venus atmosphere. And this is an absolutely out there crazy idea. Venus is so hot, its surface is too hot for life of any kind, we think. But just like here on Earth, if you hike up a mountain or go on an airplane, it gets colder and colder as you go higher in the atmosphere. So on Venus, 50 kilometers above the surface, that's so far, right? 50 kilometers in the cloud layers, it's just the right temperature for life. And not only that, we have life in our clouds on Earth. Bacteria get swept up from the surface and they spend about a week in the clouds before they're rained out. So those two things together make it like, wow, okay, maybe this idea has legs. But the Venus atmosphere is a horrible environment. The clouds are not water, but they're made of acid, sulfuric acid. It's so horrible, it destroys all our Earth life, and it's very nasty. Anyway, so someone connected our two teams, and Professor Jane Greaves invited my team to join hers. That's how I got involved with working on phosphine. So in the year 2020, right during the pandemic, we made a big announcement that we discovered phosphine in the atmosphere of Venus. And we said that we wrote 100 extra pages on what could be making this phosphine. Think of like lightning or meteorite delivery or volcanoes. Nothing checked out, honestly. Many methods do make phosphine, just not enough to explain the observations, not enough by a lot. This result became immediately controversial. It's really hard to find the signal, and people questioned whether the signal is real. People looked at the data, used their own techniques to analyze it in a hurry. Some of them didn't find the signal. Others did find the signal, but then said it's not phosphine, it's going to be sulfur dioxide. Others believed the signal, they believed it's the report of phosphine, but they wrote quick things on how phosphine could be produced without life. So for each one and that's what science is supposed to do. People are supposed to be skeptical and push back. So for each paper that comes out that says the signal's not real, or the signal is not phosphine, or it is phosphine, but there's a non-life explanation, our team goes back and responds to that in the scientific literature. So there's been this ping pong. That's what science does. People don't realize it, because if you Google phosphine, you just get the news that it's dead, it's over with, it's not there, it's wrong. But it's actually still going back and forth, actually.
So you were able to reply to the other papers and other groups. Do you think then that there still is phosphine, or are you doubting the existence of phosphine on Venus?
Well, I stand by my team's results that there is phosphine on Venus, but that not everyone will agree with that statement.
Yeah.
And
And
honestly, like if you want the honest truth, ultimately, we probably have to send a probe to Venus, a mission to Venus to go into the atmosphere and measure phosphine. I don't know if we're going to solve it from here on Earth.
yeah, it's always a probability, right? Based on your materials and methods. And so if there, it doesn't necessarily imply that there is life, but there's a good chance it might. Then how do you imagine it? Is it, like you said, the bacteria in the clouds?
The really amazing thing about phosphine right now is not the phosphine debate in and of itself, but what phosphine did for Venus. Because this whole thing was, it was like a giant tidal wave. And now it shone a new light on Venus, and it brought new people into the field. People have taken a fresh look at old data. People are creating new models, and we now have missions to Venus, which we never had before phosphine. And one of the things that my group has done, we started to do some chemistry in the laboratory. And we took some complicated biomolecules and put it in sulfuric acid to see what would happen. And lo and behold, we found a lot of biomolecules are stable in sulfuric acid.
Which is insane.
It's insane. A lot of biomolecules are not stable, but it's insane to think of having sulfuric acid instead of water and to be able to have life based on, like, it's still so insane right now. It's still early, so I can't, we don't have enough information to say whether this is legit or not, but it has nothing to do with phosphine. This is like a whole new field in and of itself, and a couple of different people are working on this, and everyone is just so astonished.
Yeah, I'm astonished as well. It sounds really insane.
In fact, like after we're done talking, I'm going to go into the lab to make a few more measurements of our latest project.
Okay, so maybe I should not stretch your time so you can go work. If you still have time, I would still ask a few questions.
Absolutely.
Also, not that long ago, earlier this year, ESA sent the European Space Agency launched its JUICE mission, where they will explore Europa, one of the Galilean moons of Jupiter. This is assumed to be one of the most promising places to look for life in our solar system. Do you think they will find anything, or do you have some prognosis of that mission?
It's hard to say, but it's pretty amazing because Jupiter's icy moons, they have water beneath the surface. And wow, they might have life as well. So everything is good. Honestly, there's so many more, not just Venus or Jupiter's icy moons. There are a lot of great candidates out there, and it's really just a matter of money and time to be able to explore them.
But we do assume, based on our experience on Earth, that we always need a liquid to have life, right?
We do. We assume we need some kind of liquid for chemistry to happen. I mean, chemistry can happen in air as well, but we need a solvent to have molecules break apart and reform.
And does any liquid work? I assume there are some limits.
Well, wow, we don't know that yet.
Yeah. Okay.
Hopefully we can answer that sometime this century.
So when we look for biosignatures, one of the biosignatures is oxygen. What are some of the other biosignatures that we might be looking for?
We have phosphine.
Yeah,
methane is another favorite, methane. But methane, many of these gases can be produced in other ways, like methane comes off of our seafloor at mid-ocean ridges. So methane is one. N2O, nitrous oxide. We have a long list, like methyl chloride. I mean, none of these might make any sense, but there's sort of a growing list of gases produced by life that can accumulate in the atmosphere and be detected afar. But the problem is many of them, life has to really be churning these things out. And a lot of them also have false positives, probably all of them, actually. One could dream up a way that they're made without life.
Okay, yeah, so that's one of the difficult parts of your research, that the gases that you're looking at that might be produced by life might also be produced without life.
Right, so there are communities trying to sort through these, and as you might have mentioned a bit, probabilities might be the way to go in the end.
So when we say, for example, we look for oxygen in an atmosphere, does that essentially mean that we're looking for some organism that is doing photosynthesis?
Most likely.
Yeah. So we're actually focusing on carbon-based life.
Well, most likely, yes, but honestly, we can't create an entire biochemistry and say this type of life produces this type of gas. So all we're going to know is that there's a gas that doesn't belong, that's in huge quantities, that we can't find any other way that it's made. And therefore, there's a good chance there's life there. We won't even know if it's bacteria, like slime, like mold, or whether it's intelligent life. We're just going to have a sign of life. We're not going to know anything about that life.
Yeah, and that's a big difference, at least in our interpretation of life.
It is, but we have to remember that, we're slowly making progress. Like before, we didn't even have proof there were planets around other stars. Now we not only know of thousands of planets, but we know rocky planets of the kind that could host life are out there. We know of planets in the Goldilocks zone of their host star. So we've come a long, long way, but there's definitely way more to go.
It's maybe a far off question, but the universe is also expanding. Does that mean it's getting harder to watch for extraterrestrial planets? Maybe not in 2 years, but in the long run?
Well, no, because I want you to think about our galaxy having lots of stars, hundreds of millions of stars, and they're all bound together by gravity. And every planetary system within their system, they're also bound by gravity. So although our universe is expanding, our galaxy is going to stay as far as we know. And so far, we can't really observe planets in other galaxies. People have some ideas of maybe how to find a planet in the nearest galaxy. But we're just talking right now about our own galaxy, and everything is kind of stuck together. So our galaxy is not stretching out or anything. It's just the space between galaxies.
Because I'm no astrophysicist, but there was also something of light bending around the sun and using that as some kind of way to magnify the
right.
The area behind.
You've done a good job.
I've tried to.
Well, that's still within our own galaxy. And not only is that within our own galaxy, but it's still around the very nearest stars. It's like you share the Earth with several billion people, but are you going to meet all those people?
Yeah, no.
I mean, you probably mostly know people in your apartment building or on your street, or maybe at your workplace or your school. We rarely become good friends with people, even in the next city, certainly not the next country. So in the search for life, I want you to think about just your nearest neighbors right now. Maybe it's the people on 2 streets over. But honestly, it's not people on the outskirts of town or the next town. It's literally just that neighborhood. So for now, we're kind of limited. And so we're not as worried about the expansion of the universe or any other problems.
So even though we have found so many planets and stars, we're still only looking 2 streets away.
Mostly in our neighborhood. We have some that are quite far away. But like the large majority of them, they're just kind of what we'd call within our neighborhood. Well, they're within, let's say, the closest few. The closest, say, 10,000 stars, let's just say. So maybe whatever your nearest, and it's a lot, I guess, your nearest 10,000. But the search for life, it gets harder. It's pretty hard. So in that case, yes, it's just your neighborhood.
10,000 sounds a lot, but if you take into account how many stars there are, I assume, yeah.
Yeah, and you take into account the transiting planets, so that narrows it down. And then it has to be the ones that are near enough and bright enough that we can follow up.
And in your search of extraterrestrial life, do you have some idea what that would look like? I've heard you talk about photosynthetic birds.
Well, occasionally we get asked to speculate, and it is just pure speculation, but we're imagining some planets with a very thick atmosphere and it's so dark. How could photosynthesis happen at the surface if no light is reaching the surface? So one idea is, imagine instead of having plants be photosynthetic, it's real ant creatures like birds that could go higher and higher in the atmosphere and spend some time doing photosynthesis. Another one we really like is if you think of a planet with very high surface gravity. Well, the opposite is, when you think of people on the moon and they're just bouncing around because the gravity is very low. I want you to think of the opposite now, a planet with high surface gravity. It would be nearly impossible to move. And people who think about these things, they do think that the type of creature that would exist are creatures low to the ground, like with giant, like elephant-like legs, because it's so hard to move around.
Oh, that's cool. But and in case, for example, of photosynthetic birds, don't they need a place, for example, then to land if they are not able to use the surface?
Well, they could land on the surface. They'd only be doing photosynthesis while aloft.
Okay.
Just like our plants only do photosynthesis during the day, not at night.
Because I was thinking, like, if a bird gets born, like the chick, it's not able to do photosynthesis. So then it's need to get food from its parent that is flying up or something.
Yeah, just like chicks right now, they don't get their own food because you know how the parents bring the food back. They spend a lot of time doing that.
Yeah. Okay. Yeah.
I mean, I don't
that's
have
cool.
it all worked out. I'm just like,
Yeah. I
kind
know.
of making it up as I go along.
Okay. Yeah, I study plants and trees and stuff. So do you think
Oh, wow.
there is a, but not in space, just on Earth for now?
Right, I understand. Yeah.
And do you think there is some possibility for plants or plant-like structures on exoplanets?
People like to speculate if there are, what are they doing with photosynthesis? Because our photosynthesis here, it's pretty specific. And people imagine these red dwarf stars, most of their light they're giving off at red wavelengths, not at 500 nanometers, but like at 800, 900, or 1,000 nanometers. So people want to speculate that they'd be using different pigments. There's a lot of work, not a lot, but there's some work in that area, just trying to think about what these plants would be like. What color would they be? How would they be getting energy from their star that has longer wavelength, like, lower energy wavelengths?
Well, but it is, like, for example, for photosynthesis, the most abundant light that their plants are using is actually red light. They're mostly using red and blue, and that's why they look green to us.
Right, but we're talking way more red, though.
Yeah, but yeah. Well, that's really cool.
Yeah.
Yeah, so we might have plants in a completely different color.
Right, they could be a completely different color. That's right.
And do you think there's a possibility for silicon-based life?
Maybe, but silicon, one of the main problems with silicon is if it locks with oxygen, like quartz, like glass, like rock, it's nearly impossible to break that silicon-oxygen bond, actually. That's a problem. So if you want to think about rocks, they have a lot of silicon-oxygen bonds. Like, how are you going to use rock for to get your silicon for your life, whereas carbon is just literally lying around, right? Carbon dioxide and lots of other things. So I'm not personally a big fan of silicon for that reason. I know science fiction fans love the idea, but I'm not really sure. I would never say never, though.
Well, just being a bit philosophical, if like silicon is also one of the main ingredients for computer chips, so in a way we could classify AI maybe in the future as silicon-based life.
Totally. I would definitely be with you on that. That's a really good way. I'm going to definitely incorporate that when I get asked this question next time. There's actually a phrase we call it post-biological intelligence.
Oh, yeah.
Yeah, and people think that, and perhaps all civilizations evolved to that. And that eventually we don't really have life as we know it anymore. Like, think about your phone. Everyone's glued to their phone. Would you have Neuralink if you could? Like, would you have someone implant a memory chip or way to just think your way through your life? Like, sure. I mean, people will. We have pacemakers and artificial limbs, and people have a lot going on. And so it sometimes seems like science fiction. Other times it seems like just a matter of time.
And imagine that happens, that we move away from biological life. Will it change something in your search for life? Would it be more difficult to find extraterrestrial life?
Probably. I mean, it probably is. We just haven't really, not too much work has been done in that direction. People like to think about technosignatures, signs of technological civilizations, but I don't know if anyone has taken this, like, where our Earth might go, if we did get overrun by AI robots that can access 3D printers, and, where would that go in terms of science? I would think they'd be more efficient, and have less waste gas. So I'm not really sure, but it's a really interesting idea.
When you say technological signatures, it's like radio waves and stuff like that?
Sometimes it's radio waves. Sometimes people want to imagine that the other life forms have built a giant structure that we could see in a transit light curve. People want to imagine ginormous amounts of city lights. You could see that from far away. Or we imagine gases, like we have chlorofluorocarbons, which are very artificial. We don't think life could produce them, but we don't know, of course. So we have that. So it's a whole bunch of different things.
That's the cause for the hole in the ozone layer, right? The chlorofluorocarbons.
Right. But there's very little, like they would be very hard to see from far away. But yes, exactly. That's it.
In your view, what would be like the largest expected breakthroughs in your field in the near future, or in the far future is also possible?
Well, the near future is we're hoping to find water vapor on a rocky planet in its Goldilocks zone. And this water vapor would be a sign of liquid water oceans. because we have to be replenishing the water vapor in the atmosphere at all times, or as we discussed, the water will break apart and hydrogen might escape to space. So the nearest sort of most solid thing, it's not life, okay, but it's habitability, is finding signs of water vapor that indicate a liquid water ocean on another world.
I hope we get there soon.
I hope so.
Before we close off, do you have a take-home message for our listeners?
My take-home message is keep an open mind. There's some crazy things out there, like this whole beginning of this journey on Venus, that people could have worked on all of this decades ago. In fact, some of the work my team is doing, when we look into the literature, some of it was done already, but people didn't know that Venus had sulfuric acid clouds. It wasn't known yet, or they just didn't think about it. They were just doing pure science and experimenting with molecules in sulfuric acid. So keep an open mind, because big things can happen.
This was the 20th episode of Apple Finch Pudding. I want to thank the amazing Sara Seager for the information, and let's meet again for the next episode of Apple Finch Pudding.